We're doing this stochastic thermodynamics of Kuramoto model. I mean, that's a plan today. Yeah, okay. So we were talking about a system which is described by a Hamiltonian. The Hamiltonian, of course, contains, so X is the microstate of the system, and lambda is a parameter that we can tune as a function of time. So to have a concrete example, the thing that we considered is the Kuramoto model in the absence of any natural frequency. There's no omega I. So in that case, this Hamiltonian will be just the potential energy with no omega I plus an external magnetic field. So as we mentioned, Kuramoto plus no omega I, this is nothing but the XY model of magnetization. So in this case, this V of theta I, so lambda is now the strength of the magnetic field, external magnetic field of strength H along X axis. You can make it more general, doesn't matter. So this is the interaction term. And then this is the magnetic field contribution. And what we want to do is we want to change this parameter lambda as a function of time. So therefore, in this setting, for example, okay, so this could be a function of time. And this, so this is an example, okay? So this is example. And what we said is that we do the change in the following way. So this is lambda of t as a function of time. So at t equal to 0, we bring the system to equilibrium, to canonical. So this is my system, and the system is in contact with a heat bath at temperature T. So we bring the system to equilibrium with the heat bath at a given fixed value of lambda, namely lambda I, and then over some time tau, we change it according to our will. I don't know how we change, so whatever we want, to a new value, which is lambda f. I means initial, f means final. And then at time tau, we stop changing lambda any further. So we keep it fixed at the value of lambda f until some other instant of time tau star. So in doing so, what I am doing is that I am allowing the system to equilibrate at this new value of lambda f. So initially at this instant, the system is in equilibrium with this value of lambda I. So this is my equilibrium distribution. And here also at this time instant also it is in equilibrium, but then at the new value of lambda, which is lambda f, so the equilibrium distribution is z lambda I and z lambda f, these are the canonical partition function. So generically you can write z lambda is integration of dx of e to the minus vector. Okay, this is the definition. So therefore, in doing this experiment, what I am doing is that I am driving the system from one equilibrium state to another equilibrium state through intervening states which are not necessarily in equilibrium, because I don't drive lambda infinitely slowly. That is, there is no limitation like quasi-static transformation, etc. So what I do is that I change it drastically, but the only thing that I do is that initially the system is in equilibrium and then I change lambda up to time tau. Lambda changes from lambda I to lambda f, and then at this point I stop changing lambda any further. I let the system come to equilibrium at this new value of lambda, and of course it would take some time. Okay, so that's why I had to wait for the time interval tau star minus tau for the system to come to equilibrium at this new value of lambda f. So therefore I am going from one equilibrium state to another equilibrium state, and I compute the work which is done, and we understood why work has to be done, because lambda is changing, so therefore suddenly the particle feels a different potential. The energy changes suddenly. So how do I find the work? So I ask how much does the Hamiltonian change keeping the position fixed. Suddenly the particle feels a different value of lambda. So keeping x fixed, how much does the energy change when lambda changes by a small amount? So this is the change in lambda in a small time dt. Okay, and then I just integrate it over the time 0 to tau, and this will give me the amount of work done on the system. No work is done in this part of the protocol because here lambda is not changing, so lambda dot is 0 here. So nothing, no contribution comes from this part of the protocol. All contribution that you get from this part, from time 0 to time tau. And what we said is that for thermodynamics and second law of thermodynamics, in particular Clausius's inequality tells you is that if you are dealing with a thermodynamic system, a system comprising many many degrees of freedoms, and then the total work done on the system is greater than or equal to the free energy change between the final and the initial equilibrium state. So what is delta F? Delta F is equal to F of lambda f t minus f of lambda I t. So how do I get F? So once I know the partition function, the free energy at a given temperature and at a given fixed value of lambda is given by minus kBt log of the canonical partition function. Okay. So this is what second law of thermodynamics tells me, that if you have a thermodynamic system comprising many degrees of freedom, then the work done on the system is either greater than or equal to the free energy change between the states that you are driving the system between. So you have equality if it is done reversibly, quasi-static reversible transformation, and otherwise you have inequality if the transformation is irreversible. This transformation, this to that, okay? And then we said that so much so for a thermodynamic system, which has many, many degrees of freedom, but suppose you want to generalize this result to microscopic system, that is a system that contains only a few degrees of freedom. So then what you would expect is that if you do this experiment over and over again, that is every time you prepare your system in an initial state sampled from this distribution, so it is in a microstate X sampled from this distribution, then you change lambda always according to the same protocol. You are not allowed to change the protocol of changing lambda. Okay? So this protocol remains the same, but every time your initial condition is different. It is still distributed according to this Gibbs-Boltzmann measure, but the precise state is different, precise configuration is different. Start from here, you change lambda, and then at this point you stop changing lambda, and you ask how much is the work done on the system. So if you repeat this experiment over and over again for a microscopic system, even for a macroscopic system, in principle you should get different values of lambda. Why different values of work? Why different values of work? Because the trajectory of the system is different. Each time you are starting from a different initial condition, so the trajectory is different. The initial condition is different, that is one source of randomness. The second source is the system is evolving in contact with the heat bath. Therefore, the dynamics is not deterministic, it is stochastic. Langevin equation or something of that sort. But even if the dynamics were deterministic, still you have randomness coming from sampling of the initial condition. So you should get different values of W, and in principle you should get a probability distribution of W, a histogram of W. Okay? And then you would think that a more precise formulation of this equation would be to say that first I compute the average W, which is nothing but dW rho W, and then W average is greater than equal to delta F. If you are dealing with a thermodynamic system, then this probability distribution will be sharply peaked. As you make the number of degrees of freedom larger and larger, the distribution will be sharply peaked and will approach a delta function. And so then when it approaches a delta function, computing the average is the same as the variable itself, because you just get in practice only one value of them. So this is what second law of thermodynamics tells you, Clausius's inequality. But then we said that okay, this is an inequality, is there a way to make it, turn it into an equality? And the statement is that if you exponentiate both sides and then take an average, then this becomes an equality. So we checked several things. First of all, this one obviously implies that W average is greater than equal to delta F using Jensen's inequality. So this one obviously implies this, but this one doesn't necessarily imply this. I may have many different forms of the probability distribution and so on. This doesn't at all imply this one, but this one is obviously true. So then we made several comments about the remarkable feature of this one. First of all, this equality holds independent of the way in which I change lambda. That is, this is one protocol, but suppose I do another protocol in which I change lambda in a ramp, as a, linearly. Then also the equality will hold. Okay? So it doesn't matter how I change it. Second thing is that this one, the right hand side depends on states that you attain at time tau star and at time 0. Okay? So this is the equilibrium state and this is the equilibrium state. So delta F refers to the free energy difference between the equilibrium state at this time instant and at this time instant. Okay? while the left hand side e to the minus beta w average, that relates to a quantity that has been computed only over this time interval 0 to tau, not 0 to tau star. There is no point in computing work over this interval because anyways no work is done. So left hand side over this time, right hand side over that time. The third thing is that what is this beta, because there is a lot of discussion in the literature as to what I should take beta to be, because after all the system is initially in equilibrium and then I do something, so there is no guarantee that the temperature of the system will remain equal to T at all intermediate times, but you have to interpret it this way, that beta is the inverse temperature of the heat bath with which the system is in contact, and being a heat bath, the temperature of the heat bath doesn't change regardless of what you do with lambda. Okay, so in that sense it is very well defined. Okay, so I will give one proof of this one for the case in which this dynamics is deterministic, because then the proof is rather simple. But if you also take into account stochasticity in the dynamics, the proof is rather involved and requires you to look up the literature and okay, so there is a huge body of literature on this one. Acha, before that, so this is known as the Jarzynski equality. There is another Acha, before I move on, let me just ask, are there questions on this one? Because it could be that some aspect of it is not clear. I mean, this equality and the average, etc., they all have to be done in a very specific manner. So if you don't understand the manner in which it has to be done, do tell me and I can go over it again. Because although the relationship looks remarkably simple, there's a lot of underlying things like how you do it and what is stochastic and what is not stochastic and so on and so forth. So if you feel something is this, I hope you know, at least this you must have read about it in your second lecture on thermodynamics, I think. Okay.
Excuse me. What is your purpose of writing these equalities? What do you want to prove?
Okay. No, it's a general, first of all, it's a general curiosity. I have an inequality coming out of fundamental laws of physics, which is the second law of thermodynamics. I may wonder, is there a way in which this can become an equality? Okay? Because equalities are always good to deal with. And secondly, you see what will happen is that typically in chemical reactions and so on, you are interested in free energy difference, because a chemical reaction takes place only when you surmount some energy barrier. You go from one state to another and there is an intervening energy barrier that you would like to know to find out whether a given chemical reaction is going to take place spontaneously on its own. So it is important to know what is delta F between two states, and then what this one tells you, it gives you a prescription of computing the free energy difference just by doing this experiment, that you start with the system in equilibrium. You see, the remarkable fact is that it doesn't restrict you to change lambda in any particular way. Thermodynamics will tell you that in order to know delta F, you better change lambda quasi-statically, infinitely slowly, so that the system at all intermediate times is in equilibrium. And then if you do it that way, if you change lambda very slowly, then thermodynamics tells you that you have an equality. So to know the free energy difference, you can compute instead the work. But the problem is that, what do you mean by infinitely slowly? Infinitely slowly meaning that it has to be slower than the slowest process that you have. So you have to allow the system to adapt itself, to relax. While you are changing lambda, you have to change it so slowly that the system is able to relax to its equilibrium state at every instant of time. But this you don't have really a handle on. You do not know a priori what are the time scales in the system. So therefore, computing free energy from work measurement by stipulating that you change lambda infinitely slowly is not a very viable option. While this one, it says you don't have to change lambda infinitely slowly. You don't care about time scales. You do whatever you want. But then you compute instead of W average, you compute instead e to the minus beta W average. So the left hand side of this equation is very easy to measure in experiment because it doesn't put any restriction on how you do the experiment, excepting for these two things that you start with the system in equilibrium. Actually just one thing, I mean and you stop somewhere, that's it. Okay, so this is the utility of this equation, and generally it's a curiosity, that you have a fundamental law of physics telling you that there's an inequality, so can I make it more stringent? Can I make it into an equality? Because equalities are always better to deal with.
It is not possible anything of this analysis with natural frequency different from zero.
Yes, yes, of course. So that will be the Hatano-Sasa equality. I'll come to that. Yes, of course. There is a so this is for a system described by a Hamiltonian. Now, when you have the system that is not described by a Hamiltonian, when the system doesn't have an equilibrium stationary state, you may ask what happens to this equation. So then, of course, there is no natural way to define the free energy difference, because if the system doesn't have an equilibrium stationary state, so then you don't know what is the stationary measure. Definitely it is not e to the minus beta h. We saw this, that for the Kuramoto model without frequencies, it was really e to the power minus beta h, because it had the form e to the power kr cos theta by d. But when you had frequencies, it had a very complicated expression for the stationary distribution that cannot ever be couched in the language of exponential something. And of course, in that case also you can generalize this. I will come to that. So that is another equality that that came into existence later than this one. Okay. Okay. Yeah. So there is one more equality that I would like to mention, which is related to this one, which is the following: that well, here what I am doing is that I am changing lambda from lambda I to lambda f according to a protocol. Okay, so let's denote the protocol by lambda t, let's say. So this is my protocol. T lies between such that lambda 0 is equal to lambda I and lambda tau is equal to lambda f. Okay, this is my protocol. This is how I define the trajectory of lambda. Not trajectory, I mean the way I change lambda. So in doing so, I do this thing and I get a distribution of work which is rho of W. But suppose now I repeat the experiment by changing lambda in the reverse direction. That is, now what I do is that I prepare the system. So let me draw another figure corresponding to this one. Can I rub this off? This part is not so relevant, I guess. Well, it is relevant, but I guess you remember what it is. So. Okay, I guess you know the partition function. So this is one set of experiments from where I get the distribution rho W. I do another set of experiments in which what I do is that again this is my time, and initially I keep the system in equilibrium at lambda f. Okay, so this is my lambda t. Initially at time t equal to 0, I keep the system in equilibrium at lambda f, and then over the same time interval tau, I change lambda, but now in the reverse direction, that is according to the reverse protocol. So let me draw a simple, okay, maybe look at this one, then it is easy. If I draw something complicated, then okay. Now I do this. It's exactly time reversed, protocol. And then I keep lambda fixed at lambda I, and again at some time tau star, it will come to equilibrium at lambda I. So what is the protocol now? Let me call it lambda bar T. Okay, this is the time reversed protocol, which is nothing but lambda of tau minus T. I hope this notation is clear. Here I am changing lambda in the forward direction in time. That is, I am increasing lambda according to a given protocol, and there I am decreasing lambda in exactly the time reverse manner. So it doesn't have to be straight line. I just do it for convenience. It could be anything. Let's say like this. So it could be like that or whatever. The only constraint is that the time reversed protocol is obtained from the forward protocol by just doing this thing. So in doing so, what I will get is I'll also get work done and the distribution and a distribution for work done. So let me call this guy the forward distribution. That is the distribution of work when I change the protocol forward in time, as in here. So this is rho FW. And this is rho RW. Okay, so then this is rho R. So then there is an equality that says, so this is the Crookes theorem. So it says, so you may wonder, is there a relationship between the work distribution when the experimenter was done in the reverse direction and the work distribution when the experiment was done with lambda changed in the forward direction? They have to be related in some way, because in the forward direction, if you do work on the system, in the reverse direction, work is done by the system. Okay? So, of course, it is not obviously related that the two, it is not obvious that the two would be related this way, but they are related this way. I hope the statement is clear. What you do is that you take the forward distribution, you take the reverse direction, the reverse distribution, take the ratio, but then you have to take W and minus W. The reason is that W automatically changes sign when you are going in the reverse direction, because work is done on the system. If you do work by the system, work is done on the system in the forward direction, backward it will be work done by the system. So therefore you make it minus, so that both these two quantities are work done on the system, and then you take the ratio, and it says, the theorem says that it has to be like this. Is the statement clear? So these are two probability distributions. What can I say about these two probability distributions from this form of the ratio? So these will be two distributions. Okay, so let's say if I draw my W, let's say this is my rho F of W, and somewhere it would be rho R of minus W. But can you tell me whether the two distributions will ever cross each other? They will cross, right? When W is equal to delta F, they will cross. So what you will find is that you will find two distributions. So this is rho F, and they don't have to be exactly the same. I mean, I'm just drawing something. And so the crossing point is when W is equal to delta F. Okay, don't take it too hard. I mean, this is just whatever I could draw. I mean, I'll show you some explicit form of the distribution. And in fact, in the assignment, I've given you a problem to compute these distributions explicitly for a very simple problem of a particle which is in a harmonic potential And then what you do is that there the tuning parameter is the stiffness constant of the harmonic potential. So the initially the system is in equilibrium when the harmonic potential is like this, and then I suddenly make the potential open up. So tuck. Okay. So this is the forward and the backward will be this. So in either case you can compute the work distribution because the equations of motion are linear. So because it's harmonic potential, so everything can be done exactly, and you can compute exactly the form of the forward and the reverse work distribution to find that they are both given by Gaussians, and then you can check explicitly that the ratio of these two work distributions satisfy this would satisfy this equality. So let me first show that this theorem implies Jarzynski equality, okay? Because they are intimately related. So one should be related to the other in some way. So let's see if this one implies that one.
Excuse me.
Huh.
For having this probability distribution for work, we have to do the changes continuously, yes?
Changes
Changing
lambda, yeah. Continuously meaning that okay, you can do it in a ramp, or you don't change and suddenly do a big change. You do whatever. I want to go from lambda I to lambda f. Protocol could be anything. For example, let me give you some examples of protocol. So lambda t. So this is my t. What is now I have been tasked with the following thing, that I start from lambda I and I have to go to some new value lambda f. What is the way in which I change lambda I so that I go from this to that is completely arbitrary. So I can do it like a straight line, I can change it in like a ramp, okay, this is one possibility, or I can keep it fixed and then do this and this is also a possibility, or I can do like this is also a possibility, whatever.
continuous.
Yeah, no, this one is okay, there is a jump here, this one. You keep fixed and then suddenly change. That is also okay. The protocol is completely arbitrary. Okay. Yeah. Okay, so let me just show you that this Crookes theorem implies or is consistent with Jarzynski equality. So how do I do it? Can somebody help me? How do I, starting from this equation, rho f w by rho r minus w equal to minus how do I go from here to this one? What is the step that I should take? Sorry, I think this should be plus. Sorry about it. It should be plus. What is the thing that I should do to go from this to that? Well, if you multiply by w and integrate, who said it? If you multiply by w and integrate, you get the w average. But I want to know e to the minus beta w average. So I multiply instead by e to the minus beta w. Okay. So let's say I do e to the power minus beta w average, which is by definition equal to e to the minus beta w times. Like let's say I want to do it for the forward distribution. Okay. So with respect to the forward one, this is by definition this is this, but then rho fw is nothing but e to the minus beta w. I use now this one rho r of minus w e to the beta w minus delta f. I just substitute for rho f from this equation, and e to the minus beta w and e to the plus beta w, they cancel. That's why you need a plus sign here. So what you get is, sorry, there's a dw. dw e to the minus beta delta f rho r of minus w. And then what I do? Why do I, how can I take this out? Yeah, this is it's a state function. It doesn't depend on, you know, it of course, I mean, there's no dependence on w anyway. But this integral is equal to 1 because this, sorry, this is just the normalization condition for the distribution. So therefore, I get e to the minus beta delta f. So e to the power minus beta w is e to the power minus beta delta. Like obviously this one is a much stronger statement than Jarzynski, okay? So this one doesn't mean that it has to be so, but if this is so, then this has to be so. So you know this thing, these you know, the theorems, they always go in one direction, that if this is true, then Jarzynski equality has to be true. But if Jarzynski equality is true, this one doesn't have to be true. It is a possibility, not the possibility. Okay? So before I give a proof of this, I will come to your question. What happens if you have the frequencies? When you cannot write down free energy difference and this and that, and then how do I generalize this? First of, okay, before I move on is the statement, and you know, now you know what is Jarzynski equality and what is Crookes theorem and so on. So these are considered very fundamental results in modern statistical mechanics, and they apply not necessarily to a thermodynamic system. They apply as well to small systems comprised by only a few degrees of freedom. You don't have to have a large number of degrees of freedom, because nowhere did I use any fact that the system is comprised by a large number of interacting degrees of freedom. So they should work also when you have a single degree of freedom. Okay, so that's why this branch of thermodynamics is called stochastic thermodynamics, because here you are dealing not necessarily with macroscopic systems. You may as well deal with microscopic systems where fluctuations are dominant. So nowhere did I use the fact that as you make the number of degrees of freedom larger and larger, the probability distributions become sharper and sharper. You have law of large numbers and central limit theorem and this and that. So we did not use. By the way, much of these results can be derived using the language of large deviations, and also notably by using the language of martingales. Okay, so this martingales this is something that mathematicians and probabilists have long known to be an efficient tool in dealing with stochastic processes, but in physics it's a rather new concept that is being extensively used. So this is okay. Shall I move on? Okay. Okay, so maybe. So now I will show you what happens when you make the system, the system doesn't have an equilibrium stationary state. Instead, it has a non-equilibrium stationary state, as happens with the Kuramoto model when you have the frequencies different from 0. Yeah. Yeah, okay. Everything is stochastic here. Okay, so let's see what are the dynamical processes which are there, okay? The dynamical process is time evolution of x. How does the microstate change as a function of time? Okay, so x refers to a configuration or a microstate of this system which is in contact with a heat bath. So therefore, the time evolution of x is, one dynamical process we have to keep in mind, and this x, the dynamics of x is stochastic. Why? Because it is in contact with a heat bath. Okay, so the equations of motion will not be just Hamilton equations. You have to put in a noise term and a dissipation term. So to say, the dynamics of x will be governed by some Langevin equation. This is one source of stochasticity. Second source of stochasticity is your initial condition is not definite, because you are sampling your initial condition from this equilibrium distribution. So this is a histogram from where you are sampling your initial condition. Once you prepare it to be here, once you prepare it to be there, and so on, but it's the same, parent histogram. Okay, so there are two sources of stochasticity: initial condition and dynamical evolution. Of course, lambda change is deterministic. I mean, I don't do it randomly. I do it according to a given fixed protocol. Okay, so now we look at the case when the system doesn't have it doesn't have an equilibrium stationary state, which is Kuramoto model plus frequencies plus, of course, an external field that I change as a function of time. Being tuned in time. External field or external, this parameter lambda. So then I ask what is the fate of this one? The Jarzynski equality. So now we come to another equality. This one is a bit non-trivial, but only a bit, so nothing to be scared about. So instead of having Jarzynski equality, so this one doesn't work, this one now works. And of course, I will show by taking a specific example that how this can be reduced to that. So here, okay, let me see the notation. Okay. So let's do it side by side so that you know what is what. So here we had the work, which was so here some part of this formula I can just copy paste. This part I can easily copy paste. But the question is, what about this guy? What is this? Because when you have frequencies in the Kuramoto model, the dynamics doesn't derive from an underlying Hamiltonian. We saw this. So what do I write for this guy? Okay. So here you write a different quantity. Am I using? Okay. I'm just copy pasting. Okay. And I call this guy Y. I better not call it W because I've done some magic here. What is this phi? Surely it's not the Hamiltonian. So this is minus log of what is this? Here, what I am doing is that here the system doesn't have an equilibrium stationary state. So when I keep my lambda fixed and I ask what is the stationary distribution, it is not an equilibrium Boltzmann-Gibbs distribution. It is some other thing, rho SS. Okay? So just to give you an example, for the Kuramoto model, we had seen what these two quantities look like. So let's say Kuramoto with no frequency, with no omega I, then we know what this thing looks like. So this one, if you recall, this one had the form e to the kr cos theta by d. Right? This was the form that we had when we had no frequencies. So this one is the equilibrium stationary state. Equilibrium and therefore Jarzynski and Crookes. Jarzynski. But the next thing is what happens when you have frequencies. With omega I. Then we had seen in the last two lectures what is the form of the distribution. The form of the distribution was something like this. It was equal to a omega e to the omega theta plus kr cos theta by d times, now I almost remember it, almost I would say, I guess it is like this. Okay, so in this case I have the equilibrium one, I know free energy, blah, blah, blah. Here, this is the stationary distribution. So what it says is that, how do I define this phi? So this phi is defined to be the negative of the logarithm of that distribution. Okay? So you define this quantity. So in this case, you have e to the minus beta w average is equal to e to the minus beta delta f. What happens to the guy here? Here you have instead e to the minus y average is equal to 1. So this is the Hatanusasa equality. You see, in this non-equilibrium case, there is no temperature factor that appears because you know it's a system that is driven out of equilibrium. So therefore, even if the system is in contact with a heat path, but there is some non-equilibrium process. So therefore, you know, the way you define it is you define it this way. I will show you that if in this setting you take a rho SS to be rho equilibrium, you will get this one. But first let us see if you understand the content of these two equalities. Huh. Well, actually this is kind of like a thermodynamic potential, okay? So the way you motivate this definition is the following. If you are in equilibrium, okay, so what will be if you are in equilibrium? So this rho, this guy, if you are in equilibrium, this would be e to the minus beta times v. And then you take the log of it, it becomes like the potential. So it is the generalization of, so okay, let's put it this way, that under a non-equilibrium situation, the stationary measure cannot be written down as exponential minus beta v, cannot be. But still what you can do is that you can always redefine your distribution as e to the minus of some potential. Okay? So that is to say that this one I can always forcefully write it as it is e to the minus beta, sorry there is no beta now, phi of x lambda. I can, this is just instead of looking at the distribution itself, I look at the exponential of a function. It's the same. No information is lost. So then if you take the log and minus, you get this. So it's just, you take the distribution and you just redefine it differently.
It has nothing to do with grand canonical.
No. You see, grand canonical equilibrium, or canonical equilibrium and so on, they all relate to equilibrium situation, because grand canonical is nothing but canonical for the particular case in which the number of particles is not a constant, but still you have this e to the beta minus beta h, okay, because grand canonical measure is e to the beta mu n minus beta h, okay, so it still has that form. Okay, so let me show that this one of course is consistent with this one, but before that let's pause for a minute and ask if you have questions. Oh, that is the equality, that is the Hatano-Sasa equality. So this is the Jarzynski equality, this is the Hatano-Sasa equality. You were interested in knowing how do you generalize this equality to the situation in which the system doesn't have an equilibrium stationary state. So the answer is this. I will show you that this one is consistent with this one, better be, because these are just two sides of the same coin. On one side of the coin you have an equilibrium stationary state, on the other side of the coin you have a non-equilibrium stationary state. So this should be consistent with that I will show in a minute. This is the generalization. If you ask what happens to Jarzynski equality when I include frequencies in the dynamics, when I know that the system at a fixed value of lambda does not have an equilibrium stationary state, what happens to the equality, Jarzynski equality? The answer is contained in this equality. Okay? So the plan is the following. I will show you that this one is consistent with this one. I will give you a proof of this one, simple proof in a simple setting, not the general proof. This proof you can read about in the original paper by Hatano. It's all referenced in the notes, so you can look them up. So these have rather long proofs.
Could you please move the chair?
This one, okay. Yeah, sure, definitely. This is fine? Or shall I write up? Maybe I can. It's okay? Okay. It's equal to 1. So e to the minus y, this is equal to 1. Maybe I should stop writing somewhere here. Okay. So let's see how one follows from the other. Okay, I'll write it again, no problem. Okay. So let's just see that how Hatano-Sasa leads to Jarzynski. Hatano-Sasa equality. Because a non-equilibrium stationary state, an equilibrium stationary, it's a special case, okay, of this. So one should follow from the other. So let's just see what Hattanusasa says. So you define this quantity. And then this Hattanusasa equality says that e to the minus y average is equal to 1, where this phi x lambda equal to minus log of rho ss of x lambda. Achha, I forgot to emphasize one thing, but I somehow thought that it is evident, so therefore there was no need to emphasize. But let me anyways emphasize, which is the following, that this one in this definition of y or in the definition of work that I had written down, the two are exactly the same, excepting that phi gets replaced with h, or the other way around. I thought this is evident, but let me anyways mention this. To evaluate this function, you see, you need to evaluate along the actual trajectory that the system follows, right? Because x is having some dynamics, so how do I evaluate this? What I do is that I take x that I get out of the equations of motion and I evaluate this function along the trajectory. That's why it was stochastic, because there were many trajectories, right? This is evident, right? I don't have to emphasize. Anyways, I emphasize, so this is fine. How do I evaluate this function? Because as lambda is changing, the actual trajectory of the particle is also changing. So I evaluate this function along the actual trajectory. That's why it's a random variable. Otherwise there was no, why would it be random? It is random because x itself, the dynamics is random. So you have to evaluate it along the actual trajectory. I thought it is evident because the way it is written. Okay. So let's take the case where rho ss x lambda is nothing but the equilibrium distribution. Rho ss x lambda, sorry. This would be e to the minus beta x lambda divided by z lambda. Then what is this function phi? This would be minus beta hx lambda. Yes, so phi was what? Phi is equal to minus log of rho ss x lambda. So I guess the minus sign becomes plus, and then I have this log of this will be minus eta plus log of z lambda. I hope I did it right. Yes, I did it right. Does z lambda contain any dependence on x? No, because x has been integrated over, right? Z lambda is just to so that's why there's no. So let me just plug this in here in the definition of y. This one. So what I get beta of 0 to tau. Del phi del lambda will be del h x lambda del lambda lambda dot dt. Now what is log z lambda? Free energy F lambda is equal to minus kbt minus 1 by beta log of z lambda. So therefore log z lambda is nothing but equal to minus beta f lambda. Okay, so I am just substituting this in here in the definition of y. So the first term would give me beta, which I pull out because beta is a constant. Del phi del lambda is nothing but del h del lambda, and the second term will be minus beta of 0 to tau del f lambda del lambda lambda dot dt. Fine. But this guy is nothing but just df lambda between lambda I and lambda f. Right? Del f del lambda lambda dot dt is del f del lambda d lambda, which is df lambda. How much does the free energy change when lambda changes from lambda I to lambda f? There is no path anything, no path, nothing, because f is a state function, which is nothing but f of lambda f minus f of lambda I. Okay. So I see that for the particular case in which the system is in equilibrium, this y quantity is nothing but beta times, but what is this guy? This is nothing but w. Del h del lambda lambda dot dt. So therefore y is nothing but beta of w minus delta f. This is delta f. So therefore when I use it in the Hatano-Sasa equality, e to the minus y average equal to 1, I just substitute it here, I get exactly Jarzynski equality. Right? So there is no mystery. It should be like this, and it is like this. So Hatano-Sasa, you can think of it as a generalization of the Jarzynski equality to the case in which the system doesn't have an equilibrium stationary state, but instead has a non-equilibrium stationary state. So the only new thing that I have to do is to redefine the quantity that appears in the integral. You don't call it del h del lambda, instead you call it del phi del lambda, where phi is nothing but the negative of the logarithm of the stationary distribution.
So looking at this by definition, it looks like it defines entropy sort of like W minus delta F times beta. Why only?
No, W minus delta F is not entropy, it is the dissipated work. No, why would W minus delta F look like entropy? So this is, W is the total work done on the system, delta F is the free energy difference. So what it says is that whatever work I do on the system, a part of it goes into increasing the free energy of the system, and the part of it just gets lost, goes for a ride. That is the dissipated work, and the way one understands it is by saying that a part of the work that you do on the system is used up in fighting against some dissipation, some friction, something. Some irreversible processes that are there, I just need to, it is expended in, doing those things. So this is W dissipated. In fact, this is the form in which the second law of thermodynamics is, you cast it like this, no? Instead of saying W delta, in books you will find this one, W dissipated greater than equal to 0. W minus delta F is not entropy. Entropy is already contained in the free energy. F is U minus Ts. Okay, so now I give a proof of the Jarzynski equality and then show some numerical results for the Kuramoto model, demonstrating how do these distributions look like and so. Sure.
In this proof, we are computing the average using the integral of rho w with the operators. So why we use that?
Which proof? Okay, let me first see. I just showed that Hatano-Sasa is for non-equilibrium situations. Equilibrium is a special case. So using Hatano-Sasa, you can get Jarzynski. But of course, Jarzynski doesn't imply Hatano-Sasa. But Hatano-Sasa, of course, is consistent with Jarzynski. In which proof did I use this one?
In the last one, in the
Passing from Hatano-Sasa to Jarzynski? Which one did I use?
to compute the average,
Yes.
we use the integral of rho, rho times the exponential dw.
No. In Hatano-Sasa, I did not do it. See, Hatano-Sasa just says that e to the minus y average equal to 1. This average is computed exactly in the same manner as you compute for Jarzynski. You keep the system in equilibrium at lambda, you change lambda, you get to a new equilibrium state at a later time, you compute the the work done by running this experiment over and over again. Each time you keep the system in equilibrium at lambda I, change lambda f according to the same protocol, and you compute y that way, you compute w that way. You get a distribution of y and distribution of w. And what this one says is that the average of e to the minus y, this of course is by definition equal to e to the minus y rho y dy. Now, like again I am lost. So here there is, and the other one was this. Where did I use? Okay, okay, hopefully I have it here. Okay, let's just do it here. You see, in the definition of y, how is y defined? Y was defined to be this guy. This was y, okay, where phi was defined to be minus log of the stationary distribution at the same value of lambda. Okay. So then what I did was, if it is an equilibrium stationary state, then rho ss x lambda has this form. If it has that form, then I just compute y. First of all, let me just compute phi. So what I have to do is I take this form and take the log of it with a minus sign in front. If I do that, I take the log and minus, this gives me that. Numerator and denominator will give me this. Okay, nothing. But this one is nothing but minus beta f lambda from the definition of Helmholtz free energy. So therefore, when I plug this expression for phi in here, I get this. Y is equal to, the first term will give me beta del h del lambda minus beta this guy. Okay. Then what I did is that I said that, look, but this is exactly the Jarzynski work. This is the definition of Jarzynski work. So the first term will be beta w. The second term will be what? Minus beta of what is this guy? This is del f del lambda lambda dot dt. There is no dependence on x because f doesn't contain x. X has been integrated over. So del f del lambda lambda dot dt is nothing but del f del lambda d lambda. Okay, so this one is nothing but del f lambda del lambda d lambda. But this I can write it as a perfect differential, which is df lambda. At time 0, lambda was equal to lambda I, and at time tau, lambda was equal to lambda f. So I do lambda I to lambda f of df lambda, which is f of lambda f minus f of lambda I, which is del f. So I just plug all this in here, in this expression here. So what I get is I get e to the minus beta of w minus delta f average equal to 1. This immediately follows this. Why? Because delta f I can pull out. Delta f doesn't depend on path. It's a state function.
It doesn't care about the...
Doesn't care. Why? Because you see delta f, this one is same as that. Why? Because delta f doesn't care about what is the path that the system takes. It is a state function. A state function has the property that it just depends on the state you are in, not how you got into that state. Okay? So therefore it doesn't matter. You can pull this guy out. So you get e to the beta delta f. You bring it here, e to the minus beta delta f. Which are the other state functions that you are aware of? Other state functions other than free energy that you know about? Gives free energy, but something other than free energy? What is the first state function that you encounter in thermodynamics? Sorry? Internal energy, absolutely. Internal energy, entropy, these are all state functions, right? And then, okay, you take combinations of internal energy and entropy, you get free energy. And then when number of particles is not conserved, then you bring in chemical potential and this and that. You get Gibbs free energy. So let me quickly give you a proof of the Jarzynski equality, because you may wonder as to how does this mysterious object come into existence, because it doesn't look at all obvious that you exponentiate and things work out. So the proof that I will provide is, of course, it was there in the original paper of Jarzynski. This is the simplest proof that you can have. So for that I need to okay. Okay, so the proof is for the following setting. So please be with me, because the proof, the setup is slightly not complicated, but you have to pay attention, that's it. This value and this is like this. Okay, so initially you are in equilibrium. And at this time also you are in equilibrium. And during this time evolution, the most general setting is you keep the system in contact with a heat bath. But now let me simplify my life a little bit by saying that initially the system is in contact with the heat bath, and I let the system come to equilibrium at lambda I, but then I disconnected the system from the heat bath. Okay? So for this length of time there is no heat bath. And then at time tau I bring in the heat bath again. At this time the heat bath is brought in again, and then system comes to equilibrium at this new value of lambda. So that is initially lambda is equal to lambda I, and the system was in contact with the heat bath. I let the system, the two guys come to equilibrium with one another. Then I remove the connection. I throw away the heat bath. The time evolution here does not take place in presence of a heat bath, but again at the final instant I bring in the heat bath and I let it equilibrate at this. So on this part there is a heat bath, initially also there is heat bath, but in this intermediate time there is no heat bath. Can somebody guess why would I like to do it? How would it simplify my life?
You're not limited by the temperature anymore?
No, the temperature that appears here is the initial temperature. So it's the temperature of the initial state which is the same as the temperature of the final state. In between the temperature anyways I did not care about, because when you see in these intermediate times the system is never in equilibrium. So therefore I cannot say in these intermediate times that the system has a well defined temperature. Whenever in Jarzynski I talked about temperature, it's the temperature here and the temperature there. Or if I keep the system always in contact, it is the temperature of the heat bath, it is never of the system.
My question is that now that we don't have a heat bath in the process, can we do a reverse thing again?
Yes, I can do the same thing I do. I keep the system in contact with the heat bath here, let it come to equilibrium, remove the heat bath, let lambda change in the reverse direction. I bring in the heat bath again here.
But like would we have this minimum trajectory again? Can we like find that trajectory which like you had the smallest, like the lowest energy you needed to spend from one state to another? Because it's not.
I did not use that fact. Where did I use it?
No, I mean we didn't, but like there was a heat bath, you had a limit, like you could just go slowly and slowly, like it.
I didn't. No, see the slowness.
But like back then, it could be an option, but now it doesn't feel like.
No, it is still an option, because that slowness or fastness has to do with how I change lambda. Heat bath is there or not there, it doesn't make much of a difference. Well, it does make a difference in the sense that if I keep the system in contact with a heat bath in these intermediate times, then the dynamics is going to be stochastic, because it's the Langevin dynamics. But now if I remove the heat bath in this intermediate time, the dynamics is going to be deterministic. So therefore I can relate one to one a final state here to an initial state here. It will be just pure Hamiltonian evolution. So that will simplify the matter a little bit. I still have one source of randomness, which is that the initial condition is not fixed. It is not one microscopic configuration. It is any microscopic configuration sampled from this distribution. So therefore, if I repeat this experiment over and over again, still I will get a probability distribution for W, because the initial state is not fixed. It is not one point. In the phase space, I have many points and they are all distributed with this distribution. I start from one and I do this, I start from another and I do this. So this intermediate times, since the heat part is not there, I can relate a state here one to a state there using the deterministic dynamics of Hamilton. Okay, so that makes the computation of the integrals a bit simpler. Okay. Okay, so let's do it. So I want to prove the Jarzynski equality. So what I do is that I start from an initial condition x0, which is taken from this distribution, rho equilibrium x lambda I is equal to e to the minus beta h of x lambda I by z lambda I. This is the particular initial condition that I have prepared my system in. Okay. Now let me compute this guy. Okay. So I've started from this initial condition and I compute the total change in the energy along the trajectory that the system follows while lambda is being changed in time, and during this evolution there is no heat path. So what do I do? This guy will be, so there will be there is an explicit dependence on time because lambda is changing as a function of time. So this would be this, and there will be a term which would look like this. I would think that this one you would know. This one you know how to get it, I guess you guys would know, but some of you would not know. What you do is that you take the derivative with respect to x and p, okay? So this is this gradient term here, and then how does x change as a function of time, right? This is partial chain rule. But then this term, can somebody tell me if you evaluate it using the Hamilton equations of motion? You see, I have to evaluate it along the actual trajectory that the system is following, and along that actual trajectory at every time instant the Hamilton equations are going to be true simply because I have removed the heat path. So therefore at every time instant the Hamilton equations are going to be true, and if it is so, if I compute it along the trajectory, what do I get? And then you get 0, right? Why you get 0? Because suppose lambda did not change. Suppose lambda did not change. So this term will not be there. So this would say how does the energy change along an actual trajectory that the system follows under Hamilton dynamics? The energy doesn't change because energy is a constant of motion. Here the energy changes only because lambda is changing. Along x nothing will happen because it's it's a property of the symplectic structure of the Hamiltonian dynamics that along a trajectory, so this is partial. This says I don't change lambda, how does the energy change along a trajectory? You get 0. Or you can do it explicitly also.
Excuse me.
Huh.
So you mean like removing that thermal pass, and now the system is isolated, and because of this the energy is conserved, yes?
1 minute. No, energy is not conserved. Energy would have been conserved. Okay, I have isolated the system from the heat path. Energy doesn't remain conserved. Why? Because lambda is still changing. See, in the Hamiltonian, there is one contribution from the microscopic states, but also a contribution from lambda. Okay? X is changing, X is not changing. But you see, if I write this out, you will get these two terms, right? The change of energy with respect to P times dP dt, and the change, right? This is by definition this, and dq dt I know it is del H del P, sorry. So, and so this is that, and dP dt is minus del H del P. So you see automatically that this term cancels out. It's just because of the Hamiltonian structure. So therefore, whatever energy change is there is the change induced by change of lambda. The explicit time dependence that is there in the Hamiltonian is causing the change in energy. Had that explicit time dependence been not there, the energy would not have changed. So therefore, when I use in the definition, when I use this in the definition of work, so this was the definition of work. Okay. But then this thing, I can write it as See, del H del lambda lambda dot is nothing but what lambda dot is, lambda, this is d lambda dt, okay, so which is nothing but this guy using this one, but this is nothing but of you will get an answer which you should have guessed, or at least I should have helped you guess it. Okay. So see what I am doing. What is the change, total change in the energy? There is a partial and there is this one, but this term is 0, okay. So now I use it in the definition of work. dt of del H del lambda lambda dot is nothing but del H del T, right? Del H del lambda lambda dot is del H del T, but del H del T is nothing but dH dt using this one. So dt dt goes away, so this is this, just this. Would you have guessed this answer? That the work done is equal to the change in the energy between the initial and the final state? You should have guessed it. Why? Because there is no heat bath. So whatever work is done, it has to go into changing the energy of the system. So this is the change in the energy computed along the actual trajectory. So x tau is the point in phase space that you get to starting from x0. And of course, if you change your initial condition, you get to a different x tau. But these two are uniquely related to one another via the Hamilton equations. So therefore, the advantage in getting to this framework is that since the dynamics, so while the system was evolving from lambda I to lambda f is deterministic, so therefore work done is nothing but the change in the difference in the difference between the final energy and the initial energy computed along the actual trajectory. And of course, when the trajectory changes, I get a different value of work. So then the proof is almost done. So this is the definition of work. So I just plug this into the Jarzynski, e to the minus beta w. Okay. So then what is e to the minus beta w? This would be what is W by the way? So W I just substitute from there. So W will be h of x tau lambda f minus h of x0 lambda I. The brackets are fine. Okay, this is my work done. Now you see, where does the randomness come from? The randomness comes from the distribution of x0. So therefore, when I am doing this average, when I do this experiment over and over again, I have to average over initial condition, because during the time evolution there is no randomness. If I start from x0, I go there. If I start from here, I go there. So therefore, this I need to average with respect to this guy. Is this point clear? You see, because I have removed the heat bath during the time evolution, so therefore, why this W is going to be random? It is because the initial condition is random. The initial condition is taken from different, it is taken from the same parent distribution, but the initial condition, once I get this value, once I get that value, etc. Once I know the initial phase space point, the final phase space point is uniquely related via the Hamilton equations. Okay, so whatever randomness is there is in here. So therefore, when I compute the average, this is W e to the minus beta W from here, I need to average with respect to the initial distribution. That's why I plug in rho ic. What is the probability that I start with this initial condition? Having started with this initial condition, this is my work done. And I integrate over all possible values of x0. Is this thing clear?
So here dw rho w is equal to re-equilibrium dx.
Yes, indeed, because you see why W is random. W is random because the initial condition is random. There is nothing in the time evolution that makes it random. So therefore, when I average with respect to the initial condition. And how am I going to choose my initial condition? I have decided to choose them from this equilibrium distribution. So I better plug in here. This will give me the probability distribution of the initial condition. Once I know the initial condition, the final condition is fixed. I don't have any option because it is deterministic evolution. So Hamilton equations will tell me, given this initial condition, there is one and only one final condition at time tau. What is the nature of the, why does it happen that, what structure of the Hamilton equations guarantees that for every initial condition there is one and only one final condition at a given fixed time? Not linear, need not be linear. First order differential equation in time, right? First order equation, so what is the form of the equation? So you have q dot is equal to p by m and p dot is equal to minus del h del q. See, it doesn't say that this function has to be, this is linear happily, but this part doesn't have to be linear. But you see, these are first order differential equations in time. If you give me initial condition, that is the initial value of q and p, these are first order. So therefore, the final condition is determined uniquely once and for all. Had it been second order differential equation, things would have been different, but it is not so. But now what I have to do is, now it's basically one line. Okay, so now I substitute for this rho equilibrium. So rho equilibrium 1 by z of lambda I, okay. Then you get e to the minus beta h of x tau lambda f minus h of x0 lambda I, okay. But rho equilibrium has got e to the minus beta of h of x0 lambda I. Like again there is cancellation, because this term will cancel that one, e to the minus beta h, e to the plus beta h, right. So you get this to be equal to 1 divided by z lambda I of, okay, there is a dx0, sorry, dx0 e to the minus beta h of x tau lambda f. So, okay, this is exact. I did not do any approximation. What I did was I just substituted for the form of rho ic. Rho ic is e to the minus beta h by z. So therefore, e to the minus beta h and this e to the plus beta h goes away. These two terms, they cancel each other. So therefore, I get dx0 e to the minus beta this. Okay. But now I can do the following thing. I can do a change of variable. Why do I need to do a change of variable here? Why do I need to do a change of variable? Why do I need to do a change of variable here in order to do the integration? Yes, exactly. This is a function of x tau and therefore this is a function of x0. So I need to go from x0 to x tau. Okay. So basically what I have to do is this is equal to 1 divided by z of lambda I of d of x tau. Okay, I do a transformation. So therefore I need to write down this Jacobian of transformation. Times whatever is there. e to the minus beta h of x tau lambda f. Fine? I go from x0 to x tau. So dx0, I use this one, dx0. You know this one, I don't have to write because it's already there. If I want to go from dx0 to dx tau, there will be a Jacobian transform. But this guy is equal to 1. Why? Because under Hamiltonian evolution, what is guaranteed is, see, this is an infinitesimal volume element around the initial phase space point. This is the infinitesimal volume element around the final phase space point. And one basic property of Hamiltonian dynamics is that the volume remains the same. The shape, it may get stretched and it may get compressed and this and that may happen, but the net volume should remain the same. Right? You take a volume element here under Hamiltonian dynamics, the net volume will remain the same. Huh? Sorry? This is exact. So you can, in the notes I have given a proof of it, but it's very simple that what it says is that you take a phase space volume element here, after some time it may become like this, it may get stretched, the shape, but the net volume, the net volume will remain the same. So therefore this guy is equal to 1, so therefore I am left with 1 by z lambda I of integration dx tau e to the minus beta h of x tau lambda f. But what is this guy? What is this integral? Partition function. Partition function, so I get this to be equal to z of lambda f divided by z of lambda I. The ratio of two partition function. But what is the ratio of two partition function? Z lambda is nothing but minus 1 by beta, f lambda. F lambda, the free energy is minus 1 by beta log of z lambda, which implies z lambda is nothing but e to the minus beta of f lambda. So therefore I just substitute it here, I get e to the minus beta of f lambda f minus f lambda I I am done. So f lambda is minus 1, which is nothing but e to the minus beta delta f. So we have therefore proved that e to the minus beta w is equal to e to the power minus beta delta f. Okay, at least for this simplistic model. Now if you want to also bring in the heat bath during the time evolution, things become more complicated, and you have to look up Jarzynski's paper, or there are books. There is a nice book on stochastic thermodynamics by Simone Pigolotti and Luca Pelletti that you can look up. With Edgar, we have also written a review written from Martingale's perspective on stochastic thermodynamics, that also you can look up. But this proof is the simplest that one can provide in favor of Jarzynsky equality. Okay, so it's about the time to stop, so let me stop. So I urge you to look at the notes, because this would also help me fix any typos that may have crept in while typing out the notes. So from tomorrow we'll do quantum dynamics, this Lindblad and so on.